Today we're going to look at linear and angular speed. What's another word for speed? Velocity, yes. So it should sound familiar for those of you in physics or have already taken physics. So we looked at arc length on Monday, and arc length can be used to analyze circular motion, which is your linear and angular speeds. Suppose an object moves along a circular path S with radius r. So here's your circular path S. That's the arc length, right? It's part of this whole circumference. Our radius is r. Okay? So the rate at which the object moves along the path is your linear speed or velocity. Okay? So our velocity for circular motion is s over t. S refers to the arc length. That's why we did that on Monday. And T, of course, refers to time. Okay? The rate at which the central angle is changing along the path. So remember, central angle means that the vertex is at the center of the circle, so that's your theta there. That's called angular speed, and this looks like a lowercase w, but it's kind of a bloated w. It's actually a lowercase Greek letter. Anybody know what Greek letter that is? It's the last one. So you have the alpha and the alpha and omega. Okay, omega is the end. So this is the lowercase omega, which looks very different than the capital omega, but that's what that is. So your angular speed, omega, which is like a curvy, bloated little w, is equal to theta over t. So that theta is your central angle, and t, of course, again, is time. Okay? So let's talk about the difference between linear and angular speed and how they don't necessarily go in hand. Something can have the same linear speed but not the same angular speed, and vice versa. So here's kind of just something I made in Word. So I have a blue circle and a red circle, and I have these yellow points that both start at like pi halves, if we want to think about it as a unit circle. So if I rotate this, if I make one full rotation, then those points, and however much time that took me, I didn't count, I don't know, we made one full rotation, those points both traveled 2 pi radians. Would you agree with that? Because it was one rotation. Did they travel the same distance? No. The one on the red circle traveled farther, right? Which means their angular speed was the same, because they both traveled 2 pi radians in however much time that took me. However, as far as linear speed is concerned, this one had to travel a whole lot faster because it had farther to go in that amount of time, right? So they have different linear speeds but the same angular speed, because those are two completely different things, okay? All right, so let's look at what we need to know. So we have to be able to come up with a theta and know how that's related to our revolutions. So one revolution is one time around. That's what I just did with those points. They made one revolution. So as far as your revolutions are concerned, once you get theta, theta is the number of revolutions times 2 pi. Because each revolution is 2 pi radians, right? Then we have one revolution with angular speed and one revolution with linear speed. So one revolution when you're talking angular speed is 2 pi radians. One revolution for linear speed is 2 pi r, meaning 2 pi times the radius. It's one length of the circumference is what that's talking about. Okay? All right, so we got to pay attention to our units here. We also have to pay attention to radius versus diameter so we don't make some ridiculous mistake. So this says a bicycle tire with a radius of 14 inches rotates at a rate of 125 revolutions per minute. The first thing we're going to do is find the linear speed of the tire in inches per minute. So linear speed in inches per minute. Your linear speed is velocity, that's s over t. So I need to find the arc length. Arc length is s equals r times theta, right? That's what we did on Monday. Our radius, we were told, is 14. I'm going to multiply that by theta. So remember, theta is the number of revolutions times 2 pi. It tells me 125 revolutions. I'm going to multiply that by 2 pi. So when I do all that, I get that S is equal to, now here's where your calculator is going to come in handy. Everything's going to be in exact form, so we do not hit the pi button. All right, but you can multiply 14 times 125 times 2. Don't forget that you have a pi. What do you get for arc length? 3,500. So it's 3,500 pi, and this is arc length, and this was 14 inches, so that's inches on there. Okay? So my velocity then is my arc length, which is 3,500 pi inches over the time. To know what their time is, it goes with whatever the revolutions were. 125 revolutions per minute. So this that many inches for every 1 minute. Then I double check in the actual question part to see what units I needed, and it says inches per minute, so I don't really have to do any conversion. I just have to write it more appropriately with units and say it's 3,500 pi and then inches per minute. Like that. Okay. When you type this into formative, you'd put 3,500 pi to get the pi. Remember, use the little keyboard-looking thing that's in the answer blank. Use that one to get your pi. Have a space, and then when you do inches, if you hit the divided by, it'll pop it into a fraction for you. It's real easy. You don't have to do anything fancy there. Just make sure there's a space there. Okay. Everybody good with that? Questions? All right. So now I want to find the angular speed of the tire in radians per minute. So my angular speed, that's omega equals theta over t. So I need to start by finding theta. Theta is the number of revolutions, which is 125 times 2 pi. So that means that gives me 250 pi radians. So when I put it back in my omega formula, I'm going to get 250 pi radians over, and again, the time, it comes from the revolution per minute, so this is for every 1 minute. And I want it in radians per minute, so I don't have to do any conversion. So my final answer is 250 pi radians per minute. Okay? Easy enough on that? Okay. All right, so now let's look at one where we're going to have to do some conversions. So first of all, it says a 16-inch diameter tire. So the first thing I'm going to do is say that means that the radius is 8 inches. So I don't do something ridiculous and use diameter instead of radius, because you definitely don't want to miss a problem because of something like that. All right. On a car is making 500 revolutions per minute. Find the linear speed of the tire in miles per hour. All right, so I'm looking for linear speed. Velocity is equal to S over T. So I have to start by finding S. S is arc length, it's R times theta. The radius is 8 times, then theta is the number of revolutions, 500, times 2 pi. I shouldn't need a calculator for this, because 2 times 500 is 1,000, times 8 would give me 8,000 pi. Do not forget your units, or your pi, and that's inches. Okay, so then I go and put it in my velocity formula. I found S, that is 8,000 pi inches over, and then this was revolutions per minute, so that's for every 1 minute. When I look at the actual question, I want my answer in miles per hour, so I'm going to have to do some dimensional analysis here, which is super easy if you just write it down and do it. Okay, it doesn't matter if you start with the inches or the minutes. I always start with the numerator, just because, I don't really know, but I need my inches to go into miles. So I'm going to multiply, and I know I can convert inches to feet pretty easily from what I know. So I'm going to put inches in the denominator so that they will cancel out, and feet in the numerator. I put the units in there first so then I can get the numbers in there right. I know that there's 1 foot for every 12 inches. When I do that, the inches cancel out, and now what I have is feet per minute. But I don't want that. I want miles per hour, so I'm going to continue with the feet. Then I'm going to multiply. I'm going to put feet in the denominator, miles in the numerator. How many feet are in a mile? Thank you. That is something you need to know. That is a life skill. 5,280 feet for every 1 mile. So now the feet cancel out, and I have miles in the numerator, which is what I want, because in the end I want miles per hour. Right. Yeah. I mean, it's dimensional analysis for any subject. I mean, it's just your units, basically conversion. Yeah, so it's like what you did in chemistry. It's probably the first time you really did something like this. And then I'm going to multiply by, so I have my miles. I need the minutes to go to hours, so I put minutes in the numerator, hours in the denominator, and I know there's 60 minutes for every 1 hour. The minutes cancel with the minutes, hours in the denominator. I'm also going to circle my pi because I'm going to let the calculator help me here, but I can't forget that there's a pi on there. So when you multiply fractions, you just multiply straight across. So in your calculator, if you hit the fraction button, then you multiply the numerator. You're going to take 8,000. You don't have to worry about the ones, times 60 in the numerator. Denominator, 12 times 5,280, and let it reduce it for you. And don't forget to put your pi back on there and your units. So I'm just going to tell you, I want you pushing the buttons, but I want to make sure we're getting the right thing. Your calculator should give you 250 over 33. If it didn't, then you did something wrong. We need to figure out what that is, which means what you write down is 250 pi over 33, and then your units are miles per hour. And whether you put miles over hours like this or you put mph, Formula will take it either way because I put it in both ways. I figure this was probably the only one where you do like an mph or something like that. But this is your final answer. Okay? What questions do you have?
Keep pi out.
Keep pi out. Yes. Do not push the pi button because it will not give you a fraction back. Everybody good? Any questions? All right. So let's look at number 4. A circular saw blade with a diameter of 9 inches, so that means my radius is 9 over 2 inches. It rotates at 2,800 revolutions per minute. Find the angular speed of the blade in radians per second. Okay? So we are looking for angular speed. That is theta over t. So theta, I know, is equal to the number of revolutions, which is 2,800, times 2 pi. And that will give you 5,600 pi radians. When I put it back into my omega formula, that's equal to theta, which is 5,600 pi radians. The time, it comes from my revolutions per minute here, so that's for every 1 minute. I want it in radians per second. So my radians, I'm good with that right now. Radians is good. I can't forget that I have a pi, but I need to fix the minutes. So I'm going to multiply that. Minutes would be in the numerator. And I want it to go to seconds, so minutes to seconds. I get the units in there first, so then I put the numbers in the right place. For every 1 minute, there's 60 seconds. The minutes will cancel out. I'm left with seconds. And so all I really have to do in my calculator is 5,600 divided by 60. Notice that 9 over 2 or 4.5, that's not even relevant when you're doing angular speed. You don't even care what it is. So we should get 280 pi over 3, and then that is radians per second. What questions do you have? Well, you just, when you type radians and you hit the division sign, it'll pop it into a fraction for you. Okay? We good? All right, let's look at number 5. A windmill has blades that are 14 feet long. So is that the radius or the diameter?
Diameter.
So the blades on a windmill, the blades come out from the center. Like they're not one big thing. Does that make sense? So the blades are actually the radius. If the windmill is rotating at 5 revolutions per second, find the linear speed in miles per hour. All right, so velocity is equal to S over T. So S is equal to R theta. We just decided that the radius was 14. I'm going to multiply that by 5 revolutions times 2 pi. Oh, that's a 25. That's not a 2 pi. 2 pi. I don't know where that came from. So 2 times 5 is 10 times 14 will give me 140 pi. That's arc length, and that's in feet. So I'm going to put it back in here. Velocity is equal to that 140 pi feet over 1 what? Second, because it comes from that revolutions per second. Right. So you go ahead and you fill out the conversions for that. Now, if you know what the conversion is from seconds to hours, you can use that. I mean, I do know what it is, but I still do it separately just so I don't do something ridiculous. I prefer to like step through it and write more if I have to, so I know I have everything correct. So it should look something like that. Then you should get 1050 pi over 11 miles per hour. Okay. Any questions? If you write it all down and line it all up, get your units in there first, this is very, doable for you. Should not be a brand new concept as far as the conversions are concerned. Any questions at all? All right, so let's look at a different way to do this, because there's a lot of formulas where you could be given different formulas and find the exact same thing. Oh goodness. What we just did is that velocity is equal to S over T, okay? So that's what I'm going to put in this first blank here, S over T. And each time we did that, we had to go find S first, which is arc length. So I could have written this as R theta over T. Would you agree that that's the same thing? Okay. And then I can rewrite this in a different form and say that this is R times theta over T. What is theta over T? What does that represent? That's the angular speed, which we represent with what letter? Omega. Yeah. Looks like a W, but it's omega. So this is equal to omega, so this really could be R times omega. So your velocity is arc length over time, or velocity is also radius times angular speed, or omega. And you can do it either way, depending on what information you're given or whatever you feel like, finding first. I don't really care. I prefer the first way, and I'll show you why in just a second, unless I'm actually given omega. But let's look at number 6, and we'll talk about that. Okay, so Ryan is riding a bicycle whose wheels are 28 inches in diameter. And by the way, there's a question on the assignment that talks about wheels. When you give a dimension on wheels, it is the diameter. I know if you're not familiar with wheels, you don't necessarily know that. So this one says it. The other one doesn't say diameter, but that's how they're measured. If the wheels rotate at 130 RPMs, find the linear speed in miles per hour in which he is traveling. So we're going to use velocity equals r times omega. Okay, so we're going to find omega first. Omega is equal to theta over time. All right, so we know that theta is the number of revolutions, 130, times 2 pi over time, and this is RPM, so it's for every 1 minute. So it's this many radians per minute. So that gives me 130, oh no it doesn't, it gives me 260 pi radians for every 1 minute. So now we are going to go and substitute that into this formula right here. So velocity is equal to, the radius is what? 14. So the radius is 14 inches. I'm going to put it over 1 just to make it into a fraction because everything's in a fraction and it makes everything line up better. Times, now I have that 260 pi radians per minute. So here's what's a little weird about this. Radians aren't technically a unit, okay? Neither are degrees. That they are ratios referring to circles, and they talk to you about angles. So we have this and actually use it as radians per minute because we're distinguishing between the fact that we know it's an angular speed, but we're saying this is in radians and not in degrees because that makes a difference, okay? Your big three for units are distance, mass, and time. So when you have this radians, when we go and substitute this in, those units kind of go away because it's not a real unit, which is a little weird, I know. And one reason why I prefer the other formula better because you don't have to overthink this so much. So this is really what we substitute in is just 260 pi. Forget the radians on there because we're going to use those inches for every 1 minute. Okay? If it's your final answer and it's supposed to be an angular thing and you have radians, then you have radians. But otherwise, once you substitute it back in there, the units kind of just go away, which is strange, I know. So then we're going to convert, right? So I want it in miles per hour. I have it right now in inches per minute. So I'm going to take care of my inches first. I would put inches in the denominator, feet in the numerator. That way the inches will cancel out, right? And that means for 1 foot, 12 inches. But I don't want feet, I need miles. So feet goes in the denominator, miles goes in the numerator. How many feet in a mile? 5,280 for every 1 mile. So then my feet cancel out, and I'm left with miles in the numerator, which is what I want. I have minutes, but I need to get that to hours. So minutes is in the denominator, I put it in the numerator so it will cancel out. Hours down here. That way I know to put my 60 in the numerator and my 1 in the denominator. The minutes cancel out with minutes, and I've got hours, and I can't forget my pi. The rest is for the calculator. You should get 455 pi over 132, and this is miles per hour. Okay. Any questions about any of that? All right, so let's talk formative for just a second. If you type something into formative and it tells you you're wrong and you are 100% sure you are right, then let me know and we'll see if we can figure this out. But what's happened to some people is, and you don't even notice that it's happening, I think, especially if you had to go back and retype something, make sure there's no space before your answer. Even if it doesn't look like there is, double check. Make sure there's only one space between the number and the units, and make sure there's not a random space afterwards by accident, okay? Because it'll count that wrong, and you can't really tell that you did it. I think that's really the main thing. There's only been one where I watched the person type it in. I know they did it right. I know they don't have any extra spaces or anything, and it's still counting it wrong, and I don't know why. But that doesn't seem to be happening a lot. If it does start to happen a lot, that's what I'm trying to figure out. But I don't think so. But if that does happen, then I can add that as another right answer. That way, whatever the computer thinks is going on will actually be okay for everybody else. But it doesn't like copying and pasting. That's why you have to use that little keyboard. Like push that keyboard and use the little thing that drops down. If there's something big that comes across the bottom, don't use that. I don't know what it is, but it doesn't work right. Okay? Make sense? We good? Awesome.